Deep on the ocean floor, countless buried microorganisms from Earth's ancient oceans have, over time, created vast pockets of oil and natural gas. The quest for these organic fuels has led geoscientists to many special places as they try to solve the complex riddle of underground oil and gas reservoirs.
4 subsets in it.
The Permian Basin in the Guadalupe Mountains of far west Texas was once the bottom of an ancient ocean. Today, it's one of the most studied marine areas on the planet. Many different types of carbonate rocks form in the oceans. What we know as limestone is one of those. Around the world, there are many oil deposits associated with these carbonate rocks. This area, in particular Shumard Canyon, draws scientists from around the world because here are opportunities to study an ancient oil reserve found nowhere else on the planet.
Another day in the office.
The Permian Reef Complex is the outcropping equivalent of some of the larger oil reservoirs in the contiguous North American continent. The unique opportunity here is that in the outcrop we can see the reservoirs completely exposed. We have a complete expanse of rock to look at the different rock types that make up an oil reservoir. Here we have about a 5,000-foot vertical exposure, what would have been a tropical reef system out into a deep water basin, all in a space of about 2 to 3 kilometers.
Charlie Cairns and Jerome Belayan of the Jackson School of Geosciences are no strangers to the Permian Reef. Each trip provides them an unlimited opportunity to literally walk through the history of an ancient ocean.
Well, definitely you can see the sponge spicules in here, which are those nice circular outlines. Typical of the deep water section, but there really are no other indicators. I don't see any trilobite fragments or other things in here. Just within that dark organic content, that's the dominant thing.
What makes the Permian Reef so extraordinary is that scientists know that what they see exposed here mirrors what can be found elsewhere deep under the ground.
You can walk a timeline from the shelf down through the reef, into the slope, into the basin, and you can basically see all the relationships that you want to understand in the subsurface, and they're all laid out like a map.
With oil getting harder to find, some scientists are using specialized land-based technology like LIDAR to help locate and define new reservoirs. Meanwhile, others are launching brand new tools to explore the bottom of the ocean. Today, without oil, our modern society would not exist. It formed from layers of dead marine life that fell to the bottom of the ocean, was covered by muddy sediment, and cooked under pressure and high temperatures over millions of years. Oil reservoirs used to be fairly easy to find, but not anymore. Oil rarely stays where it forms. Every bit of information gleaned from a potential location where oil might be deposited is needed to find its precise location. More often than not, it's like looking for a needle in a haystack. And the haystack is made of layers deep within Earth. Fossil fuel reservoirs lie hidden deep in Earth's subsurface. The closest way we come to seeing these reservoirs is through reflection seismic surveys. Using sound waves, seismic images create a picture deep in Earth that can only be seen by the most sophisticated instruments. Runa Musum is a researcher skilled at deciphering 3D seismic profiles.
Up here we have an air gun that emits a strong sound signal that travels through the Earth, and every time it hits some sort of a bed boundary, it's going to bounce and echo back to the surface. And we record the echo, and we use that to help us map what's in the ground.
In the past, seismic images were two-dimensional and limited in what detail they could provide. Now, new technology allows scientists to visually move through a cross-section of Earth through time and space, much like MRIs used in medical imaging.
And I'm just going to start playing this data set, and you'll start seeing a number of things going on.
The oblong shape appearing center screen is a salt dome. This is a geologic formation that puts geoscientists on alert when looking for petroleum. Salt domes are a legacy of ancient seas that dried up in prehistoric times. They left vast reserves of salt that eventually were buried under sediments. Scientists know where they find salt, they may also find oil and natural gas. But detecting salt presents another set of problems.
It gets really hard to see.
Even deeper where the image gets bad too.
Yeah.
The reason it's hard to see beneath the salt domes is that salt has a very different composition than the surrounding rock. It deflects the seismic signal. This has forced scientists to come up with another way to visualize a more accurate picture of these salt bodies. Computers aren't always able to solve all the problems. This one requires observing nature directly. But time, geologically speaking, moves too slowly. So scientists must create experiments that speed up these processes. Tim Dooley has a real talent for building these types of models. This model represents about 500 miles of the northern Gulf of Mexico. Each grid equals 1/3 of a mile and provides scale. The different colors of sand are the different layers of sediment. He uses silicon gel as a substitute for salt because it has a very low viscosity. Over time, it flows like a liquid. Tim has found that silicon gel acts just like salt, but moves over a few days instead of millions of years.
Hi, Tim.
Martin Jackson studies salt tectonics and the formation of oil and gas traps. Tim's models provide him with excellent examples of Earth's processes.
So we're looking from one lobe across.
If you could look at salt deposits over geologic time, they often behave more like a fluid than a solid. In these images from the rugged Zagros Mountains of southern Iran, salt has ascended in fluid-like plumes, pushing through the overlying rock, forming salt plugs. What looks like glaciers is actually salt. And where large salt formations are found is where scientists look for reservoirs of oil and natural gas.
Green one. Yeah, that's.
Using time-lapse photography, Martin and Tim review the progress of what happened to the seafloor during their 3-day experiment.
And this is the overhead movie.
Yeah, look at that sudden surge initially.
Yeah.
Okay, creeping along.
Slowly.
There's another one.
There's another load.
The colored ribbons plot the direction of the salt migration.
Yeah, now we've got a suture down.
The boundary, or suture, where the two lobes meet, represents the formation of a subsurface pocket.
And down the
In nature, these salt lobes would be difficult to comprehend because of their vast size. The model brings the details into focus.
We're discovering just how common salt structures are, just how much they've deformed sedimentary basins around them. And those structures are helpful because they not only create traps, but they create the pathways for migration of hydrocarbons. So having seen the model that Tim made in the lab, we can recognize things that we might not have known before.
The scientists now take the information from the model and combine it with the 3D seismic profile. The pink shape represents the salt dome, and the red area at the base, the oil reservoir. With this more complete picture, they can now plot the drilling path to the reservoir. This pre-planning is so precise, it allows them to come within several inches of their intended target when they actually drill in the field. In September 2006, all of these technologies came together to help find a new oil reserve under a massive salt dome in the Gulf of Mexico. It could be the biggest domestic reserve since the Alaskan North Slope and potentially boost the U.S. oil and gas supply by 50%. Today, new technologies can literally peel back the layers of Earth, revealing more details of how our planet works.